Thanks. Hi, everyone. We are starting recording. Excellent. My name is Josh Persi. We're going to be talking about environments today. I have to be outside on my patio today because my home office is out of commission. If you hear traffic and it's really bad for the recording, let me know and I can find another corner of my apartment to nestle up in.
Your headphones
Okay,
seem to be working because you sound
great.
great.
Great. The noise cancellation is doing its job. I am going to pull up my screen and you should now or soon be able to see the slides, and I can see my speaker slides. Okay. So environments. I chose this chapter because I struggled with a environments related task like 6 weeks ago at the outset of this book club. So environments are new to me. You are going to be learning with me as opposed to from me. The learning objectives today, as I understand them to be, we will learn how to create, modify, and inspect environments. We will recognize certain special environments.
We don't
Oh,
see
sorry.
that slide. If you want to
Oh,
advance.
oh, okay. Sorry. I am trying to share with you the slides and then see speaker view. I guess it's not working for that reason. Anyways, thank you for that. The learning objectives are to create, modify, and inspect environments, to recognize special environments. We'll give those names later on, but there are certain environments that power some features in R that are good to know about. And we will, by the end of this session, hopefully understand how environments power lexical scoping and namespaces and other things, at least I took for granted as just being like how R works. So these slides are broken up by subsections of chapter 7. First section is environment basics. The R object that environments most resemble are lists. They behave much in the same way in that you can put basically any object type in them. They do not need to be the same object type. But there are certain differences between environments and lists. In an environment, every name must be unique. That is not the case in lists. You can have a list element share a name with another list element. The names in an environment are not inherently ordered with a like integer index, if that's the right way to put it. Whereas a list does have an inherent integer order, and that allows for certain things like integer subsetting. We'll touch on that a bit later. An environment has a parent in almost every case except for one. And environments use reference semantics, which means they are not copied when modified, whereas meaning they have the same memory address when you modify them, whereas a list, if you modify a list, I believe the memory address changes. So it uses copy semantics, not reference semantics, if that's antonym. To hit our first objective, our first learning objective of learning how to create environments, we'll use rlang. That is a package that chapter seems to use almost exclusively. There are, of course, base R ways to create environments, but two functions you can use to create an environment from the rlang package are the rlang env function, where you can specify the parent, rlang global env, and then you create objects bound to certain values. So you create an object A, which is bound to false, B, which is bound to the character string A, C to the float 2.3, and D to the vector of integers 1 through 3. By default, you don't need to provide the parent environment argument for the rlang env function. It defaults to making the environment a child of the current environment, which in many cases, if you're working interactively, is the global environment. I've just specified it here for, I guess, your knowledge. You can also create an environment with rlang new environment. It has a slightly different syntax where you specify the bindings as a list, and the parent is the parent of this environment, unless otherwise specified, is the empty environment, which we'll discuss more later. But it's like the only environment without a parent. It's the root of your environment path, if I understand correctly. There you go. Two options with rlang to make a environment. The main job of an environment conceptually is to bind, to be a place, a bucket, a box, however you want to think of it, where values are bound to names. And again, these have no implied order, unlike a list. The bindings live within the environment. So I just want to talk about these graphics because we'll be using them throughout these slides. The environment here, oh, I didn't know I could do that. I don't know how I did that, but can you see the blown up version of that graphic?
We can. Evidently, I have Lightbox turned on and didn't realize that.
Okay, that's Lightbox. Interesting. So I don't know how I did that, but while it's up, you can see that the gray box here is the environment. The parent of the environment is represented by this little blue circle. These objects here, A, B, C, and D, are the names of objects within this environment. But the values that these objects represent are actually not within the environment, if I understand how assignment works correctly. Like they're maybe more abstract, but you're just using the names A, B, C, D within this specific environment to bind or refer to a value that technically lives elsewhere, I think. So that's why the values here are shown like false. And oh, I did it again. 1, 2, 3, those are outside of the environment, I believe, as opposed to being drawn inside the environment. Because environments use reference semantics, which is unusual for at least like the data types that come with R out of the box, you can make environments contain themselves. So that's what this diagram here is showing. You have D, the object D within an environment, which points to the same environment. That is brought about by a command that looks like this. But this is an area I'm not fully aware, or I don't have a great understanding of this, but I thought that would unleash a chain of like infinite recursion all the way down where like you would forever have an environment nesting itself within another environment, nesting itself within its parent environment, nesting itself within its parent environment. But I don't think that's how this works. It's like a shallow recursion, I think.
I think that if you did E1 $D, you could add $D infinitely. But it doesn't exist that way. You're just referencing it that way. And I think that's why that works.
Okay.
So yeah, I think it does create this infinite recursion, but only if you make it. Like if you decide to reference it that way. I do know, so shiny sessions are environments. And if you're working with modules, they create a they create a session from the main session that is focused on that module. But within that child session, there is, I can't remember, it's like parent session or something. And so I was trying to think, have I ever seen anything like this? And that's basically this, that it's containing, because that child session is in, it's inside of the parent session, which is inside of the child session,
Okay,
just for referencing. So
that
yeah.
that confuses me, but something to dig into, I suppose, if you really
Yeah.
want to know how what this is trying to, what the use case here is. All right, next slide. So create environments. Now let's inspect our environments. A few different commands from rlang. You can print your environment in a nicer way. If you just use base rprint, it will print the memory address, which is this bit up here. Sorry, folks. Give me 2 seconds. I need to grab my laptop charger and plug it in. I will be back in less than a minute. Okay, back. So using envprint from rlang gives you some other nice things that base rprint doesn't. You can see the global environment, or the parent. In this case, it's the global, and you can see the bindings. Rlang env names gives you the names of those bindings, A, B, C, D. Rlang env has, it returns a Boolean for if that environment has a binding of that name, in this case A, which it does if you look up here. You can, don't know why. Oh, yes. Okay. Env get is returning false here because that is the actual logical value of A. It does not return a
That's a
Boolean by
confusing
default.
example.
Yeah. I'm not sure if that's one from the book or if I added that one in, but it returns whatever the value is of the object. In this case, it happens to be a Boolean. It does not return a Boolean necessarily. And then you can see the parent of your environment by using env parent. And there you go. It's the R global environment. There are many other functions within rlang to inspect and learn more about your environment, but this is hopefully enough to get you rocking and rolling. By default, the current, so there are two, maybe our first two environments worth naming are the current environment and your global environment. The current environment is where you are, where the execution is currently happening, I believe. And the global environment is the environment where you as a human are like working with your R session. By default, they're the same thing. So if you just open R, open Positron or Studio, get an R session going, you're in your global environment by default. If you do, you will enter into and exit out of different environments depending on whether you're running a function or doing a Shiny process or something like that. But by default, if you open up R, you're in your global environment. And by default, therefore, the current environment you are working in is your global environment. So they're the same thing by default. The current environment changes depending on whether you're entering into an R function or changing the environment some other way. But global environment is, in a sense, kind of like your home, although it is not the root in the sense of like a file directory environment search path kind of thinking. There you go. One thing I noticed about the rlang function is I don't know enough about its design, but you'll notice sometimes all the functions are prefixed with env, and other times they're suffixed with env. So I was like hitting rlang env global to try and get my global. You got to do rlang global env. I assume env underscore functions like return something about an environment, whereas current env and global env return something about like session or state.
Current env, global env is like fetching that object versus env underscore whatever is doing something with like I think the first argument for all the env underscore functions is an environment. Yeah.
Okay. Cool.
That's an interesting point that they don't all like fit together.
Just checking my notes, seeing if I have anything else to say on this. Nope, we're good. So where are we now? We've talked about creating environments, inspecting environments, learned about the current global environment. The next thing we should cover is that every environment has a parent environment. This allows for lexical scoping, which is, if I remember correctly, the thing that R does where if you can't find a value or an object in your current environment, it looks up an environment to the parent, and then it goes to that parent's parent and all the way up the environment pathway, which we will touch more on later. But it's an important, knowing that every environment has a parent environment might not sound super like useful knowledge, but it does power a super useful thing in R, which is lexical scoping. So if we just create some simple environments here, E2A and E2B, and then for the E2B environment, we're saying that the parent is the E2A environment or environment, yes. Then if we ask, what is the parent of E2B? It says E2A, which you'll have to kind of take my word for it because I think it just returns the memory address, but this is the memory address of E2A. I thought it was kind of odd that it only returns the memory address.
It's returning the environment, which in base R, which prints as the memory address. But if you assign that to something, you would be getting a reference to E2A.
Could you expand on that? I'm not sure I follow.
So when you call env parent, it's actually returning E2A. And then by default, since you're not assigning it to anything, it's printing.
Gotcha.
And the base print just shows, that's why they have the env print.
Yeah. Okay, I think I get that.
Which is confusing, which is why they have that function.
Yeah. Okay. So you're saying if I wrapped E2B, if I did env print, if I wrapped line 5 in env print, I would see
whole print of E2A, what it contained and where its address, whatever else was in print.
Mm-hmm.
It doesn't. It still wouldn't show you E2A because technically E2A is just a name. It's not the environment.
Okay. Yeah, that makes sense as to like why it can't be. I still want it to be.
Yeah.
So this I guess chunk of code here displayed visually is shown down here. Let me see if I can do that lightbox thing again. Okay, so great, it does. So it's double control twice to bring it up, at least for me. So this is our E2A environment in the middle here, the one with D and E in it. And is that right? Let me go back and double check. So yeah, that's right. So this is our E2A environment, and we are telling R when we make the E2B environment over here on the left that we want E2A to be its parent. So that's why we see this blue circle, which represents the parent, pointing to E2A. That's just how you visualize parents. So every blue dot that's filled points to, theoretically at least, another box that is another environment, which in itself has a blue dot representing an environment that points to a box. I think that's everything I had to say on this slide. The one exception for this rule that every environment has to have a parent is the empty environment. And it is the last environment on your environment search path. It is kind of like the root of all environments in a like file directory sense. You can't go any higher than the R empty env. You can use it as the parent of environments just by calling empty env. So here we're making E2C a child of the parent empty environment, and then E2D a child of E2C. So we see that this environment has a parent, which is this environment. This environment has a parent, which is the R empty environment.
So is the parent of the global environment the empty environment?
It is not. The global environment is actually, we'll touch on this later, but it is several environments above the empty environment. There are default packages like the base package, which is an environment, the auto loads package, and some other packages that are loaded by R by default that basically create space between the empty environment at the root and the global environment where you as a user are trying to use R. But that's an excellent question.
Interesting.
Hopefully it'll be a little clearer. I think there are some decent diagrams that show it later in the slides. There are at least in the book, but we can touch on that a bit later as well if there's still confusion or discussion to be had. Yeah.
Quick question. Why we
Please
have
go
an
ahead.
empty environment? I mean, why that exists?
That's maybe a tougher question. I think like kind of unsatisfactorily based on my limited knowledge, like everything has to stop somewhere. So maybe the empty environment is just like the logical place to start, just like you have like on a Windows computer, at least like the C is like the C drive is like the root of your everything you do on your computer. But I don't know if anyone has a more satisfying response as to why.
That makes sense.
It's hopefully okay. If it makes sense, I'm glad.
Yeah, thank you.
Yeah, nothing. Yeah, it's you need something. I think that's pretty much it.
So it's basically environment is nothing like a folder in Windows, right?
Sorry, could you repeat that question? I missed the first part.
It's like maybe I'm just thinking that the environment is something like a Windows, where sorry, on Windows it's like a folder. Within one folder, there could be another folder inside it, and another folder inside it, right? So
that's how I think of it, at least.
Instead of even though like we return the memory location, exactly the memory location, but behind the screens, the folder itself have a memory location. Even though we can't see it, I mean, we got so used to it saying that this is just a folder on C drive, but internally it is a memory location that has been allocated to that.
A warning or a maybe even helpful thing to think there is, you know, if you've ever worked with like symlinks or aliases of folders or that kind of thing, those happen a lot with environments that like, yes, it's like a folder, except it's like every, you know, you could give E2C another name. You could say E2C2 gets E2C, and those two things are the same thing because it's referenced in semantics. Like if you edit E2C2, you're also editing E2C.
Wow, I didn't
which
know
is
that.
different than folders. Yeah. So I think we'll get to that in a little bit, but that is what makes them really weird for R, because like, you can make a bunch of copies, but they're all the same thing. You're just assigning new names. But it's also what makes it really useful for things like Shiny or like, well, other things that we're going to see, but where you want to be able to pass this object around. And if you change it anywhere, you're changing it everywhere.
Okay, that's actually very
Mhm.
helpful for me, because I guess that's just like what reference semantics means. Like whether you're talking about
Yeah.
an environment that has reference semantics or some other theoretical R object that has reference semantics. If you update it in one place, it updates in that other binding as well, because it's bound to the same memory address. Yeah.
Exactly.
Okay. Cool. Good to know. So empty environment, the only one without a parent. It is like the last call when it comes to the environment train. So this is this will maybe be helpful to you, Nick. All environments eventually terminate with the empty environment, because it is like the last environment. It is the root environment in a sense. If I have an environment here, E2B, and I ask to R to give me all of the environments that are its ancestors, its parents, it gives me, I think this one, which is E2A, but then the rest will make more sense. We have the global environment. So its parent is the global environment, whose parent is the stats environment, whose parent is the graphics package environment. These are mostly packages. The GR devices environment, utils environment. Down we go until we get to the empty environment. So all of this stuff before globals is loaded by default when you open R. That's why you can like just open a fresh session and type in like mean and give it some arguments, and that just works. You don't need to call base or load the base package, because your R session does it automatically. So the last thing I want to say is that environment parents by default doesn't include the empty environment, because it's kind of, I guess, a weird environment, but you can force it to include the empty environment in its output by saying last equals rlang empty environment. Do you have anything you want to say, Nick? It looks like you might be queuing up for a response.
No, I think it's very interesting. Yeah, no, this is great. This is extremely clever.
Okay, cool. Cool. Then let's keep rocking and rolling. Anyone else jump in with questions as you have them. The next thing to talk about is super assignment, which is what we call this double chevron hyphen command. It is different than the regular assignment, which is most of us are probably familiar with, the single chevron or lesser than symbol hyphen, which creates a variable in the current environment. Whereas super assignment does a few things, and I'm not sure if I fully understand them. But if it modifies the variable, if it exists in a parent environment, so not in your current environment, but in the parent of your current environment. And if one does not exist in your parent environment, it creates the variable in the global environment, no matter how far down like a series of child environments you are. I think that's how it works. I tried to get some code running to like prove this to myself, but I wasn't quite able to. does anyone have any thoughts? Maybe like, did I say anything that's obviously incorrect? Did anyone catch anything?
I didn't catch anything, but like the super assignment, I never know how to call it, is used sometimes when you want to implement a counter. Like you want to implement something like that counter is going to live outside of an environment, I mean, outside of the function, and you want to do that. That's where I have used it once or twice.
I've done the same.
And I think there's a case where I used it was like when you have some kind of big function that you want to parallelize. Sometimes that's similar to a counters, I guess. But yeah, I don't know if others have used it outside of that. I don't know.
I seen once where the default value, I mean the value he wanted to override the value, but is coming within the function from the value outside the function. So he was trying to write a loop, something I really don't know, but he was trying to override the value that's being supplied outside rather than inside. And that's what I was thinking.
Almost always a bad idea to use super assignment. But like if you search for it, I don't remember how you have to escape it on GitHub, but you can search on GitHub and find the cases, like search within the tidyverse org or search within the rlib org, and see the few places where they use it. It's like, oh, okay, yeah, I can see that. That makes sense. That you, or again, like Shiny is my go-to for environments because it's very much like it couldn't exist without the concept of environments. And there are times in Shiny, again, mostly in the underlying code, where it intentionally assigns something up a level from where you're currently working. I'm trying to get a quick example to share. Let me see. There. Let's let me throw this in chat. It might look all broken unless you widen the chat window, but oh, and even then it only goes so wide. So if you assign it, like, assign something within a function, the idea is like when you call that function, that thing gets assigned. We could make a deeper nesting, and you could see that happening. Like if testing called a function that did the double assignment, then it would assign it in the environment of the testing function, or of the call to the testing function. But yeah, it tries to go up and find, tries to find it up above, and if it does find it, it'll edit it. And as Jim pointed out, it could be a few levels up, but it finds, oh, there's X here, out in the global environment. So
okay,
it's a weird case. I think he has some cases eventually where it's like, oh, okay, yeah, that makes sense. I can see why we're doing that.
We cover it in function factories, a later chapter.
Oh, yep.
I think that's what the book said.
Yep.
Okay. Let's move on from super assignment because makes my head hurt. This is maybe just more relevant to inspecting environments, but this is where in the book this is covered. Retrieving environment variables with the $ operator, the double bracket notation, or rlang functions. Because these are objects that don't just exist in rlang, they're obviously a base object type. You can use typical base R syntax. You can use the $ to get the X object from E3 environment. You can use the double bracket notation to get the same variable, but you cannot do integer indexing like this because unlike lists, environments do not have an inherent order. So it doesn't know what the first object is, the environment, so it can't return it. And you cannot use a single bracket notation. So if you want to do this, use the double brackets. Don't use the single brackets. All right, brief tangent, tangent aside. Let's keep going. You can bind environments or add bindings to an environment using the same kind of techniques, $, double bracket, or some rlang specific functions to poke. Like, I guess if you're like a needle person, you're like inserting, stitching stuff. I don't know. You can also use rlang and bind to add multiple objects, multiple bindings at once, and you can unbind them again using an rlang function. So keep those in mind when you're trying to inspect your environments.
So is poke a shorthand for bind?
I'm not
Or
sure if shorthand is how I would put it. An
Is it
alternative
just
if you
one?
just need one thing to be bound.
Oh, okay.
Yeah,
That's my understanding.
Yeah.
the difference is like the name can be a variable when you're using poke. And so you could do funkier things that way. That goes back again to the idea that environments are like folders, because at least the first time I learned poke is it's for like file system stuff, especially in Linux. You can poke a file to like update its timestamp. And so I think that's why that's called and poke. Then again,
Okay.
that poke command might be named after a programming concept. I don't know which direction it goes in.
Okay. There are two, when you're binding a object to your environment, you can use those functions we just saw, those techniques. You can do two funky things with binding. You can do lazy binding or delayed binding. I think both ways of saying it mean the same thing, where the binding, the object that is bound, the object you are trying to access via that binding is evaluated for the first time that it's accessed. So this is useful for like loading large data sets where you want to make that data set available, but you don't want to take up memory. So I think this is kind of the same concept that is used by the auto loads package, where like data sets like Iris and all the other base R data sets are made available to you, but I think they are like executed or instantiated only when you call them. So they don't take up a ton of memory. That's my understanding of a lazy binding, but you can do it in rlang if you have a specific use case. The second one is the active binding, rlang and bind active, which means that the binding is recomputed every time they're accessed. So you get different values every time you access that object. It could be the time, the weather, anything else that changes, and would give you a different value. Okay. That's the first subsection, 7.2. We're over halfway, so I'll try to be mindful of time and finish this at the hour. Recursing over environments. This is an example in the book used to find where in your environment search path a particular object might be. I don't know if I would ever need a function to do that. I don't know if there's a use case for it, but I did find the idea of recursion interesting. I've never really recursed in my data science day job. I iterate a lot but I have never recursed, and they're different concepts. Recursion, you're like going into the same thing over and over again until you, in this case, find, or you're calling the function on itself. Anyways, if anything I just said interests you, maybe you also would be keen to learn about recursions, and I will leave you to look it up just for time's sake.
Yeah, I had a super hard time understand recursion until like I took my time, and it's worth it.
It's worth
Especially
it?
if you,
Okay.
yeah, if you want to iterate over a list and stuff like that. Instead of iterating, it makes our codes usually easier to read. And it's
Okay.
yeah, it took me time.
Okay.
When you find
Okay.
it a case where it's useful, it's very useful. Like this is a valid version of, I want to keep digging through this environment or the parent environment of whatever environment I'm in until I hit the empty environment or find things. And that can happen with like something like Fibonacci numbers, like Jim said in the chat, but it can happen with like finding something that's in a nested list. You might recurse through that.
Okay.
I don't know. I can't think of examples. I've used it, and I can't think of an example right now, but
Like a JSON.
yeah.
Yeah. Any like nested objects could probably
Yeah.
recursion.
It's hard. It's unfortunate. Like I like to search GitHub to find examples of things, and it's really hard to search for recursion because it's like, you're searching for a function that calls itself.
Yeah.
There's
Yeah,
you could do a fancy regex to get there, but it would have to be really fancy. So yeah.
If I remember correctly, like in the internal or R, they still use like the Lispy Coulter CDR. That's type CDR, and they use it to recurse a list in C. So they implemented it C to work on a list. I can try to find the example. Hopefully I will find it. But it's in C here.
Okay. Recursion. Cool. Look it up if you're like me and didn't really know what it was. Special environments. These are like the named environments that every time you use R, you are, or like they're there at least. Before we start naming them, the search path, I've said that word a couple of times. It is the concept of where R will look for objects. It is basically whatever packages you have added on to, like through library calls or other ways of bringing in a library, and starts at your R global environment. Then it looks at your most recently called package, like dplyr or whatever, and then your second most recently called package, and then your third most recently called package for however many packages you load in your session. And then in truth, it actually has some other packages that are loaded by R itself before we get to the base environment, and then we terminate in the empty environment. So this is just where R is searching for variables, returning the first, in many cases, returning the first find, but we'll touch on that a little bit in it. So every time you are loading a package, you are in essence changing your search path, because that new package, which is theoretically right here, needs to slot in between your global environment and your most recently called package. And this just shows what I was saying. Attaching packages changes the search path. This is our search path with no packages loaded, by me at least, by the user. But then if you call library rlang, you'll see that rlang is now the parent of the global environment, and there's some proof for you. Functions enclose their environments. That is why they are sometimes called closure in warning messages that aren't always the most helpful. But a closure, I think, is basically a synonym for a function, at least in R. And by enclosing the environment, I mean that they capture so if you have an object defined as y gets 1, when you instantiate the function f equals function x and you use y in that declaration, in that assignment, in that function, it encloses the environment, and the environment contains y. So that's why you can call our function. That's why you can call this function f, and it knows to use y as it is. I think I've worked myself into a hole of poorly phrased explanation, but to save myself and to run on top and to keep going, the functions enclose their environment. That is how they know where to look, I think.
Yeah. Probably an easier, I mean,
Can you save me, John?
well, a clearer example would be like if in that function you say y is 7, then the y inside of the function is 7. It doesn't care that the global environment has a y that is 1, unless you don't have a y inside of the function, and then it'll go up to parent environment and etc. until it finds y. But yeah, the enclosing environment, the fact that it encloses an environment is how you can like have locally scoped variables inside of the function.
Okay, gotcha. Yes, that is more helpful and straightforward. Thank you. Refer to John if you have questions on that. I'm sorry, I realize I've maybe talked too much, so we only have 8 minutes left. So functions enclose their environments. There's the book written about it. You can refer to it there if need be. There are odd things you can do with enclosing your current environment where the function is bound to one environment, but it is being bounded in another environment. The distinction probably doesn't matter for 99% of your day job, but if you want to understand it, I would encourage you to go to the book and see if you can understand it there. Every package environment has an underlying namespace environment. The namespace contains everything that the package contains and some extra functions that aren't exported to you, the user, via the package. This is detailed in like the namespace document file. If you've ever created a package or looked at one, you can see what is being exported into the namespace or into the package environment, excuse me. And that's where I'll leave it there. As you can see with this is a function here, this yellow rounded rectangle. It is associated. This is the this is the standard deviation function. It is associated with 2 environments: the package stats environment and the namespace stats environment. And it knows when you call the SD function to look into the SD namespace and the package namespace first for any objects that might be defined. This is a bit of a Goliath graph to understand, but it shows you if you're calling a package or calling a function like SD, where SD is trying to look for objects. It first goes to the namespace, for that package from which that function is defined. Then it goes to another special type of environment the book doesn't talk about much, called the imports stats environment. Then the namespace of base. And then it goes through your typical search path, as we've shown it earlier, starting with the global environment, going to your loaded packages, going to base, and ultimately terminating with the local, with an empty environment. So an odd thing I'm getting from this graphic is that the base namespace is being called twice, I believe, or being searched through twice.
It's the namespace versus the package of base, I think, is what we're
Okay.
seeing there. But I didn't know, like, so that would, like, the namespace includes unexported functions. So that means you hit unexported base functions, which I don't know if there are such things really. Kind of, I guess. Methods mostly. But yeah, so that's interesting.
Okay.
So that, basically it means that base doesn't really have unexported functions, because
Yeah,
you're going to look in its namespace, and so you're going to see those unexported functions. That's the interesting part to me of this, and I'll have to kind of play around and see. But I think that is because of, like, the unexported functions of base are like specific print methods, and yeah, like you can see that those get searched because method is fetch. So it's
okay.
interesting. Yeah. Yes.
While I've had a chance to stall and think about this graphic a bit more, one other thing that I got from it is that this picture shows that if we have var defined in our global environment, it doesn't really matter when we're calling SD, because var is first found in the namespace stats environment. So you will not run into bugs or issues, or you shouldn't at least, if you call var like something odd that the function isn't expecting, because it'll never use that. It'll use the first var found according to this search path. Functions use ephemeral environments for their execution, or their execution environments. This is why you can have a fresh start every time you run a function, regardless of what you define within that function's body. The execution environment is a child of the function environment. Yes, they disappear. So if you assign an object within a function, it's using standard assignment. It does not exist in your global environment once you exit out of that function. Okay. We have
a question.
Oh yeah, please.
How would we remove objects from the environment if we need it? Like, say, if I mess up with a function, you're saying that it's always going to stay in the execution, right? So how do we delete with the same RM function would do that, or would that still have a copy of it behind the scenes?
The function environment is garbage collected, so deleted, removed once the function exits, successfully or not.
Oh, okay.
So you shouldn't need to ever remove something manually from your function environment.
Got it. Thank you.
We've only got 2 minutes left in the hour, so I apologize, everyone. I should have managed my time better. But if you have to hop off for another call, I totally understand. I'll try to wrap up in the next few minutes if that's okay with everyone. This graph just shows functions use ephemeral execution environments. They don't persist in your environment afterwards in your session. I won't walk through the graphic, but if you want to understand its nitty-gritty, it's there for you. Call stacks are the next subsection. call stack is a sequence. If you never called it, it's the it's a sequence of functions that are called by another function. So in this case, if you have, we declare our object, our functions over here. If we call x at 1, because we've added lobster CST, the call stack trace function, we, as the last, I guess, call in this function stack, it prints out in order of execution what we've called. So we called f at the f function, then that f function called the g function, that g function called the h function, and the h function called lobster CST. So it shows you the sequence in which your functions are being called, useful for debugging. Base R has traceback, which lets you do the same thing. But it's flipped. I'll leave that for you to explore. The call stack gets more complicated with lazy evaluation. I personally don't have any takeaways to pass on to you from here, other than I think the separate branch down here that gets introduced when you have lazy evaluation is a different environment, and that's why it's a separate. Actually, I don't think that's true now that I just said that. I'm not sure what the separate branch here entirely means. It might just be a separate function that was not nested within these function calls above. If anyone has a quick message to correct or refute what I just said, feel free to speak now.
So it's, once you get to D, you're evaluating X. Before then, you're not evaluating X. And then when you evaluate it, F, you're doing that F call in the global environment. And so that's why it jumps back up. Because
Okay.
F gets
Okay.
evaluated in the environment where you were calling from.
Okay, so each of these is like, because of the function and execution environments, each of these is getting into its own environment. Like the B function gets its own environment, which is a child of the A environment.
Yeah, the words, I don't know what the word global in these is doing. I guess it's because that's where those functions are defined. So
Yeah,
but
I'm not
like,
sure.
Yeah, okay. Yeah, it's saying where the function is defined, but then the tree is showing like where the call happened. And when you call F, it goes back up to the same place where A of F was called from.
Okay.
Yeah.
Okay, thank you. Thank you, John.
Yeah.
This is a diagram that is meant to help illustrate the call stack and how environments work with the call stack. I will leave it to you to look at. R uses lexical scoping, not dynamic scoping. There's a chapter from earlier in this book that has this quote, which basically says this fact in other words. But for us, I think it's important to know because lexical scoping means we look up the search path to find the definitions of our objects, whereas dynamic scoping, I think, no lived experience with a language that has dynamic scoping, but based on Google, it says that my understanding is that dynamic scoping uses the definition of those objects kind of as they exist in your global environment. So not only do you need to know how like the function is defined, but you need to know how the state of the environment if you want to get the same output. R doesn't use dynamic scoping, so if you're like only an R person, you might not need to know the distinction, but interesting from like a computer science perspective. Very last slide. There wasn't much on this section, so it'll be quick. Environments are useful as data structures. They have uses, including avoiding copies of large data because they use reference semantics, managing state within a package, Again, I think that has something to do with the reference semantics, but a use case beyond that wasn't provided in the book, at least from my reading of it. And as a hash map, the only thing I think I can say about this is hash maps run in constant time. And I think that's what means looking up objects in environments takes the same amount of time, regardless of how big your environment is. Because they use hash maps. That's speculative. I have not proven that to myself with like running code, but was trying to give you guys any sort of like meat on the bones. So this slide was a little more satisfying. Okay, that's everything I had. Very sorry again for going over time. I have time if folks want to hang around and chat more, but any questions, concerns, corrections, anyone would like to mention?
It's definitely a complicated topic. So I'm impressed that we got through it in just about the right amount of time.
Okay. Well,
Looking at the
yeah.
slides, I was like, I don't know, we might split this. And then, you know, it was close enough that it wasn't worth splitting. So,
Okay. Okay.
But yeah, it's
I have a
it's strange.
sorry.
You know, it's hard to wrap your head around. Sorry. Yeah, go ahead.
No, I think I have like I don't know, an underlying question of what is the practical use of environments in a data science day job. I don't know, like I'm doing some data frame stuff and analyzing data, using models. There's any use of this in that context?
I would say that, you know, if you are writing functions to do that, it is really useful to understand how environments work so that you'll know where something like what the function that you're calling is going to use. You know, if you define it locally inside of the function, it'll use the value that is there. If you don't define it there, it'll go up a level. So knowing all that. And then occasionally, like the case of if you have some giant object, putting it into a stable environment and then referencing, you know, like say that you define that object in the global environment, and then intentionally any function call you do, you reference that copy of the object instead of just, you know, explicitly say, I want the version of it that's in global, or I want the version of it that's in my packages execution environment or whatever, so that you don't have to keep reloading it. Like it is that one copy that you're using. There could be cases where that makes sense. But I think it becomes a lot more useful when you are doing like package development, something that a lot of the tidyverse packages do, or just that team in general, their packages. They'll have an environment for the package where they can put things about like the header2 package, which is for accessing APIs. It has a function like last request, I think, and then it has last response, and it has things like that. And in the package environment, whenever you make a call to an API, it puts the request that you used into last request. And so, or into the, you know, the package environment as the last request. And so last request always, that function is always just looking into the package environment and finding the last thing. That kind of functionality can let you do some really cool things. Can give you some short-term memory, basically. And I could see in a complicated analysis, I could imagine wanting to set up that kind of thing so that you can keep track of like what has happened recently. It's a case where it's like when you run into a case where it makes sense, it's like, oh wow, this makes sense. But I can't come up with a good example off the top of my head. And I would say, like I've said a couple of times in here, these rlang functions, like if you search for envpoke or envget or new end within the tidyverse org, you can find examples of like clever programming tricks, basically, of, oh, that's how they use these things. Okay. But again, that's more in a package development context than a day-to-day use. And I think a lot of advanced star is going to be getting into where you're doing things that are more complicated than what you have to do day to day. Like you're doing all these things. It's just that you're doing it by calling packages. And they, you know, it is useful to know them because you'll get to some point where you're doing something and you're like, man, I wish that this call way downstream could edit the same thing that is being edited here. It's, oh yeah, if I use the same environment, then I can do that. So I can't tell you an example, but at least now you have the tools to recognize it when something comes up.
Yeah, debugging's been a big, like understanding environments a little better helps when you write a function to process some data and it doesn't quite work right or it errors out. And it's like, well, way down that like understanding the environments when you look back at the trace for the call stack really helps to try and debug where things are going wrong. So that might be where you'd encounter it. For me, most often in the day job stuff is when you write a function to do something and it breaks, and understanding how things pass through the environment or the scoping of where it's getting that comes from really helps.
Cool.
Yeah, thank you. Those are really great answers. Thank you.
All right.
Right.
That wraps it up for me. So I think if there's anything else, let's just, take the discussion over into the Slack, and I'll see everybody next week.